Welcome to the second portion of Chapter 11, which we have been discussing certain topics related to traffic safety, and those topics would cover safety studies, statistics, as well as programs. This is here the presentation outline that we have seen last time. We started with a brief introduction about accident rates and the history of the amount of accidents that we tend to see in our country per year, and the amount of fatal accidents and injuries, and how did it decrease from the 1960s, which was about 50,000 people. Nowadays, in the last decade, we observe about 40,000 people. And we also covered last time the approaches to highway safety, as well as the accident data collection and the record systems. In this lecture, we will be talking about the accident statistics as well as the site analysis. So, accident statistics are good measures, or sometimes we tend to call them good estimates of the number and severity of these accidents. So it's not just about the number of accidents, we need to know also how severe are those accidents. In so many locations you may have several accidents, but they're not so severe compared to another location that they may have experienced one or two accidents, but they are severe and they have been associated with different injuries and different fatality as well. So that's something again we will discuss now, and we need to have a fair look into those accident numbers and how can we use those type of statistics to draw our conclusions. So speaking of statistics, there are three types of statistics that cover accident studies. First one is accident occurrence. So the accident occurrence would relate to the numbers as well as the types of accidents that occur, which are often described in terms of rates based on population, or it can be also based on vehicle miles traveled. So that's the accident occurrence statistics. When it comes to the accident involvement, those type of statistics, they are concerned about the number and types of vehicles and drivers involved in the accidents, with population-based rates. The third type of statistics is the accident severity, which is related to the number of fatalities and fatality rates, that they are typically often used as a measure of the seriousness of the accident. As I said before, you can have several accidents, but if they are not associated with fatalities or injuries, that's a good thing, and therefore we need to come up with another statistics like number 3, that is to do with the accident severity. How severe are those accidents? There are common types of analyses that are included in any accident study. First would be the trend over the time. For example, are we seeing at this intersection a trend of increasing or decreasing accidents? Second is the highway geometric elements. So we need to make sure that we are including this in our analysis, is the geometric elements and the geometric design of the highway is a reason of improving or making the situation even worse. We also need to look into the driver characteristics, including gender and age. Does this make a difference? Do we see a relation between some sort of accidents and certain age group or certain gender? Also the contributing cause. What's the cause behind that type of accident? All the way to the environmental conditions. We need to know where was the weather conditions, where was the pavement conditions at that location, and are they related to the amount of accidents reported at that location or not. So let's start again with the assumption that let's use just a simple statistics. What do I mean by simple statistics? That means if I were to compare two cities, for example, big city that has 5 million people and a small city that has 100,000 people. So let's say the big city that has 5 million people, they are having 120 people die on their network, while the small city has 100 people die on their network. So if you are doing a simple statistics, you would say, well, the small city, there are only 100 people died on their city, therefore the city is safer to drive on that network. But in reality, you need to look into the amount of fatalities over the population. of that city. If you divide again that 100 people over 100,000 people, the rate would be way higher than 120 people in the bigger city over 5 million people. So we need to again to look into those type of detailed statistics rather than a simple one, because as I said, simple statistics will cite total number of accidents, involvements, injuries, and they can be quite misleading because they ignore the base from which they arise. An increase in the number of highway fatalities is in a specific area from one year to the next. It has to be matched against population as one of the reference points, or the vehicle usage patterns to make any sense. For this reason, many accident statistics, as you would see in different textbooks, are presented in the form of rates. So what are those types of rate? The very first type of rate that we use in accident statistics is population-based rates, and those include area population. As I said, if you have certain amount of fatalities, you divide those by the area population, and that again will tell you how many injuries or how many fatalities are we experiencing per maybe 100,000 people. The second type of population-based rate is the numbers of registered vehicles. So again, that will tell us if I have a city that has 1 million registered vehicles versus 50,000 vehicles, this base number, this population-based number, would tell us quite a bit of significant information by dividing the number of fatalities and injuries over the number of registered vehicles. Same thing for number of licensed drivers, as well as highway mileage. So those are again related to population in a way or another. They are very useful in quantifying the overall risk to individuals on a comparative basis. There is another type of statistics. In this case, we call it the exposure-based rates, and those include the vehicle miles traveled and the vehicle hours traveled. Those tend to be a good measures and statistical numbers that tends to use the amount of travel as a surrogate for the individual's exposure to potential accident situation. So how do we come up with these numbers? How do we get those rates? There are common bases for accidents and fatality rates that they are used across the traffic engineering profession. For example, when it comes to the population-based rates, they are generally stated according to the following. First, if it's done based on the population, the area population, it's going to be done as fatalities, accidents, or involvements per 100,000 area population. When it comes to registered vehicles, we typically get the rate based on every 10,000 registered vehicles. When it comes to the licensed drivers, the base or the common base would be per 10,000 licensed drivers. And when it comes to the miles of that highway in that city, it's gonna be the number of fatalities or accidents or involvements per 1,000 miles of highways. When it comes to the exposure-based rates, they are generally stated according to the following numbers. First, I can divide the number of fatalities, accidents, or involvements per 100 million vehicles miles traveled, or it can be per 10 million vehicles hours traveled, or 1 million entering vehicles, and that's mainly used for intersections. So let's have an example here in how can we compute accidents and fatality rates. So the following are a sample of gross accident statistics for a relatively small urban jurisdiction in 2008. You can see those are the given numbers. So we're going to have number of fatalities. We have 75 people died, and the fatal accidents were 60. Injury accidents were 300. The PDO accidents, has to do with the property damage loss. So we had 2,000 of those, and we have total amount of accidents 4,100. The vehicle miles traveled at this city is about 1.5 billion miles. So when it comes to registered vehicles, it's 100,000, and when it comes to licensed drivers, we have 150,000 drivers, and the area population for this city is 300,000 people. So in general terms, all rates are computed as this following simple equation. The rate, whether it's a population or an exposure rate, is going to be the total number, which is the total number of accidents, involvements, or fatalities, times the scale over the base. The scale is the scale of the base of statistics as X vehicles miles traveled, for example, while the base will be the total base statistic for the period of the rate. So let's take the very first example, and how can we get the very first rate? So rate number 1 can be done using the number of deaths or number of fatalities per 100,000 population. So how can we do this? First of all, we would use this equation, which is the total, which is 75. This is the 75 fatalities, times the scale. This is the non-scale. This is the fixed scale that we need to remember, we need to use, because this is a known scale in traffic engineering profession, over the base. And that's the number that's coming from this city in particular. They had 300,000 people. So you would get this number. So if you have 75 deaths for 300,000 people, that means the rate that every traffic engineer can relate to is I have 25 deaths per 100,000 population. Second rate has to do with registered vehicles. So I can use the same thing. I can use 75, this is the total death, times 10,000, this is the scale, if you go back to the previous slide, over the 100,000. Where did you get the 100,000? This is the base. This is the 100,000 from here. This is the registered vehicles in this city. So if you multiply 75 times 10,000 over 100,000, you could tell that I have 7.5 deaths per 10,000 registered vehicles. A third rate would be the ones related to the licensed drivers. So I can multiply 75 deaths times 10,000, that's the scale for the licensed drivers, over 150,000 licensed drivers in this city coming from right here. So I could tell now that based on these numbers, I can say that there are 5 deaths per 10,000 licensed drivers. When it comes now to exposure rates, and that's represented in the last rate here, rate number 4, I can get the rate of accidents and fatalities per vehicle miles. So same thing, 75 times 100 million vehicle miles over the base. So I'm experiencing here this number, 1.5 billion miles. So from here you could tell that I have 5 deaths per 100 million vehicle miles traveled. Now I can move to another type of accident rate, which is the severity index. Severity index is the number of fatalities per accident, as simple as this. So it's a simple rate that relates the number of fatalities over the number of accidents happened. So for the data that was shown previously in the previous slide, there were 75 fatalities in a total of 2360 accidents, and that's going to lead us to the SI, the severity index, which is equal 75 fatalities over the number of accidents, and that shows us that we have 0.318 deaths per accident. So, and that's again, that's the third type of index that we use in terms of accident rates and accident studies. Now, after we do the rates, we can also talk about how can we display these accident rates. So, as you could tell here, we have in this graph number of years from 1915 all the way to 2005, and the y-axis would show you the statistic. So, which is here, it can be the number of accidents, for example. So we were able, as we discussed last time, a declining death rate since the 1970s. So one of the reasons was the imposition of the national 55-mile speed limit. But the more practical reason that kept us going until now is really the improved highway and roadside design, as well as the improved vehicle design. But the problem that we're still seeing in this graph here, that there's still continuous increase in vehicle miles traveled. So you could see that the death again would go up and down, and now it's pretty much fixed since the 70s. So the 70s and 60s, they were high. As I said here, this is the high number versus what we're experiencing here, and I think this is the number of deaths, the y-axis. So we used to experience about 50,000 people die, and now it's around 40 or 41,000, and this number has been stable again in the last decade or so. But what's increasing is this one right here. This line shows us that our vehicle miles traveled is keep increasing every single year. That means there is more exposure to driving, and therefore there is high chances for having more accidents and more fatalities and more injuries. But again, that's not happening based on what we see here. So as you could tell, in the last 10 or 20 years, the vehicle miles traveled is increasing, while the accident rates and the accident fatalities and injuries are pretty much stable. And again, that's because of the improvements that we have been making on highways and roadside design, as well as improving the vehicle design. Another type of statistics here that we like to do in certain locations is we need to identify high accident location. We can do all the rates that I talked about in the last couple slides, and from the city perspective or from a state perspective, but sometimes you have one or two headache locations, intersections at your city that they have high accident rates, and you want to make a distinct conclusion that this location is really has a significantly and from a statistic point of view high accident rate. So how can we do this on certain locations? So those locations with accident rates in the highest 5% of the normal distribution would need to be distinguished. So how can we do this from a statistical point of view? If in a one-tail test, the value of the z for, again, probability, now we're going to probability and statistics. So in one-tail test, the value of z for probability of the z less than 0.95 is equal to this number. If you go to the bell-shaped curve that we typically see in a one-tail test, we would need to look into that highest 5%. So that's why we say the value of the z for probability of the z is less than 0.95 is 1.645. The actual value of the z for a given accident location can be computed as follows. Z is equal to x1, which is the accident rate at that location, minus the average accident rate for locations within the jurisdiction under study, over S, and that's the standard deviation of accident rates for locations within that place. So if the value of the z must be at least 1.645 for 95% confidence, the minimum accident rate that would be considered to be significantly higher than the average may be taken to be, that's x1, this is what we experience at that location, they have to be higher than 1.645s, which is 1.645 times the standard deviation, plus the average accident rate. So once we locate an intersection that has amount of accident rates higher than 1.645 times the standard deviation plus the average, that means this location has a significant amount of accidents. So if I want to put it more into a graph, so this is the normal distribution. Now I'm saying this is the average, this is the x prime, and now I'm saying this location, I would say it has a significant amount of accidents, more than the typical average of the city. If it's right here, that means this distance is 1.645 times the standard deviation. So that means if any location is higher than the average by 1.645 times the standard deviation, this means this location would need to be looked at because it has significant amount of accidents compared to the entire city. So let's have an example. So let's assume that we have a major signalized intersection in a small city has an accident rate of 15.8 per 1 million entering vehicles. So this is the location. It has 15.8 per 1 million entering vehicles. The database for all signalized intersections in the area indicates that the average accident rate is 12.1 per 1 million entering vehicles, with a standard deviation of 2.5 per 1 million entering vehicles. And the question here is, should this intersection be singled out for a study and redefinition? So we need to look into it and see is this location is having a highly significant amount of accidents compared to the average of the city. So what do we have? We have the number for the certain location is 15.8, and we need to see is it far away from the 12.1, which is the city average. How can we do this? Now we need to testify that the 15.8 is it higher or equal to 1.645 times the standard deviation, which is 2.5, plus 12.1, and the number is 16.2. In order to qualify that this location has a significantly higher amount of accidents, the rate for that location has to be 16.2 or higher, while what we see in our location is only 15.8. So based on this, and using the 95% confidence level, the observed accident rate does not meet the criteria. And I want to point out again, does not meet the criteria for the conclusion that this location has a highly significant amount of accidents compared to the city. So how about if the standard deviation is low? So if we have a low standard deviation, maybe it's going to be a different story, but for now we have to have at least 16.2 per 1 million entering vehicles location in order to call this location need to be looked at and further improved for future design. Another way also of looking and identifying high accident locations is by plotting the entire intersection or the entire location. This is here an example that shows pretty much lots of streets and lots of intersections, and all what you can do by just plotting the fatal accidents and other accidents, and whether they are motor vehicle versus pedestrian or other motor vehicles or other traffic. As you could see, this is what we use to identify what type of accidents are these, and by plotting all these types of accidents at the city level, you could easily go and look at this intersection, for example, and tell that there's a lot of accidents happen at this location. And you could tell what type of accidents. You can see here they are not fatal injuries, but they have injuries. They can have vehicle loss, and the type of the accident is other motor vehicles. It's not motor vehicles versus pedestrian. Same thing again with this location. You could tell also very easily and by looking at the picture what type of accidents are there and the frequency of the accidents. Now let's talk about the site analysis. So assume that you find a location that has been statistically identified as a high accident location. Now the next step is to come up with a detailed information that is required in two principal areas. First, we need to know the occurrence of the accidents at the location in question. Second, we need to know the environmental as well as the physical conditions existing at that location and make a conclusion whether those conditions are related to the accidents or not. In order to do so, we need typically to come up with two primary graphical outputs to be prepared. The very first one is the collision diagram. Second is the condition diagram. And as you could tell, these two types of diagrams are answering the 2 points above here. The first one, the occurrence of the accidents, is going to be related to the collision diagram, while the environmental and physical conditions is going to be answered by knowing and seeing the condition diagram. So let's take a look at these two diagrams and how can we make conclusions at that location. First of all, collision diagrams. As you could see here, I'm showing a schematic representation for all types of accidents occurring at a given location over a specified period. And when I say specified period, this is usually ranges from 1 to 3 years. That's what you need to show for a certain site analysis. And typically this is what's used in traffic engineering profession. Those are the symbols and what do they mean. For example, a single arrow, that means this type of vehicle type is passenger car. If I have the same arrow but there is a T on top of it, that means the involved vehicle, it was a truck. If there's a B, that means it was a bus. If there's a C, that means it was a bicycle or a motorcycle. O, that means it's an other. If I have a dotted arrow, that means this accident involved a pedestrian. So again, the first portion of this table shows the vehicle type that was involved in the accident. The second portion here talks about the movement symbols. What happened at that accident? Were there a turn, a left turn? Were there a right turn? Were there a straight movement? Then we also we need to show in this collision diagram the severity. Did I see a property damage only type of severity? Did I see an injury severity? Did I see a fatal incident? Also, we need to show in the collision diagram the accident type. So if we see that type of two back-to-back arrows, that means it's a rear end accident. If we see two arrows heading towards each other, that's a head-on accident. These two types of two arrows that they are making 90 degrees, this shows and indicates a right angle accident. And again, it goes all the way with different types of accidents. So by looking into the vehicle type, the movement symbol, the severity of the accident, and the type of accident that happens, if we make use of all these symbols and we can put them in one diagram on that intersection, we could see lots of information at looking at one single picture. This is here an example of a collision diagram. So this intersection has experienced, based on what you could see, primarily rear end and right angle collisions. So right angle collision, as you could see, those are making the 90 degrees, and lots of rear end, as you could see here, there. Pretty much in all the locations you have rear-ended collisions. How about injuries or fatalities? We could see that the majority are several injuries but no fatalities during the study period. How can you tell? From just looking at the diagram, you could see those circles, that they are empty circles. If they are full circle, that means it's fatality, based on what we saw in the previous slide. And also sometimes this type of diagram can be coming with a small table beside it to show the accident summary. As you could tell, there's no fatal incidents, but we have 5 injuries, and we have much more than this, about 3 property damage only during the day, 10 during the night, and that's gonna give us a total of 13 PDO and 0 fatalities and 5 injuries, so a total of 18 incidents. As you could tell, another thing that we can show from this little table besides the collision diagram, that many of the accidents appear to be clustered during nighttime. You could see 6 at daytime and 12 during nighttime, so the number of accidents getting doubled at nighttime. And that also might tell you some of the reasons. Maybe the lighting conditions at that location is poor, and we need to work on it to improve the sight distance during nighttime. Now shifting gears to a condition diagram. If we look at the exact same intersections, but now I'm interested to describe all the physical and environmental conditions at the accident site. As you could see in this diagram here, we need to include, first of all, the signal locations. timings, locating all the stop lines and crosswalks, because maybe pedestrians has something to do with the accidents rate at this location, and even the location of the roadside trees, which could sometimes affect the visibility of the signals. So as you could tell, we could show that there's even gas station, there's a medical center, and here we could see a bank, and there's a parking. Again, those people are going to be leaving from here and trying to join in the stream right away. That also can be a big effect on having a rear end accidents. So based on taking a deep look into these two diagrams, I were able to sum up some of the conclusions if you take a deeper look into these two pictures, and I put them here. So how can now you interpret the condition and the collision diagrams? For each type of accident, 3 questions you should ask yourself, and you should come up with answers as well. First, what driver actions led to the occurrence of such accidents? Second question is, what existing conditions at the site could contribute to the driver taking such actions? And the third question would be, what changes can be made to reduce the chances of such actions taking place? So as we saw from the two diagrams, especially the condition and the collision diagrams, rear end accidents occur when the lead vehicle stops suddenly or unexpectedly, and or when the trailing driver follows too closely for the prevailing speeds and environmental conditions. The condition diagram also shows a number of driveways allowing access to and egress from the street at or near intersection itself. As I told you, beside the bank there was a parking, and that parking would lead very closely. Once you leave the parking spot, you would be super close to the intersection. Maybe we need to change that entrance of the parking to be a little bit away from the intersection location. Another thing that we could see from these two diagrams is unexpected movement into or out of these driveways could cause main line of vehicles to stop suddenly. So because of these driveways and stop lines are located well back from the sideline, particularly in the northbound direction. Also, vehicles as a result now are going to be end up stopping at positions not normally expected, and following drivers may be surprised and unable to respond in time in order to avoid the collision. And that's why we have there's a great amount of work that can be done here. There's a potential corrective actions include closing some or all of these driveways and moving the stop lines closer to their normal positions. That could help improving the situation. Other potential cause of rear end actions would also be the signal timing. Do we have a sufficient yellow or all red interval? Sometimes if we do not have enough all red or yellow time, we're going to have issues, and we're going to have those rear end actions. Signal visibility. If we have lots of trees or something is blocking the driver's views, that's going to be an issue too. We need to clear the intersection. Roadway lighting, is it adequate or not? Apparently in this location it's not. We have double amount of accidents during night time compared to daytime, and that again shows you that there's something that needs to be fixed at night, and that's mainly the road condition represented by the amount of lighting. Finally, there is also, we could see few right angle collisions that indicate a breakdown in the right-of-way assignment by the signal. Signal visibility must be checked at this location. Looks like that's a big issue here, and the signal timing examined for is it reasonable or not. So we can take a look at the parking openings. We can, instead of making them too close to the intersection, we can move them away. We can work on the signal visibility, and we need to check that. We can take a look at the signal timing, and again, insufficient yellow and all red intervals could release vehicles before the competing vehicles have had the time to clear the intersection. So that's also a possibility. In conclusion, again, if the allocation of a green is not reasonable, some drivers would typically jump the green or otherwise disregard it. At this location, some of the causes compound each other. The step back of stop line to accommodate drivers, for example, with the lengths the requirements for all road clearance intervals, and therefore it's going to amplify the effect of a shortfall in this factor. So as you could tell, based on this chapter, in conclusion, we were able to talk about accidents, how did we improve the accident rates, and how did we decrease the amount of fatalities in our network from 51,000 in the 60s all the way to 40,000, and how can we come up with certain statistics for the city level or for the state level. And then also we got to learn how can I do statistical analysis to see if I have a high accident location, and how can I prove this from statistical point of view. And lastly, if you can come up with the conclusion that this location has a significant amount of accidents, how can I further study this by plotting and drawing the condition and the collision diagrams and look into the reasons of the accidents and how can we correct it. With this, we finished chapter 11. Thank you so much.